Across the silent theater of the cosmos, sudden, cataclysmic shifts shape everything. These are the universe's tipping points, moments when balance breaks and unimaginable energy is unleashed. A star erupts in a solar flare or collapses in a hypernova, outshining its galaxy for a brief, brilliant moment. These events forge the very elements that make up our world. On a neutron star, the crust can crack, sending ripples of gravitational energy across space-time. The energy released in an instant can dwarf what our sun produces in 100,000 years. The night sky's stillness is an illusion. Beneath it lies constant cosmic tension. Gravity pulls matter together, while nuclear fusion pushes outward, an endless dance of opposing forces. When this balance snaps, chaos gives birth to new wonders, stars, planets and objects that test the limits of physics. We live in the aftermath of these tipping points, our very existence a product of cosmic crisis. The universe is a tightrope walk of opposing forces. In a galaxy, gravity pulls stars inward, while their momentum tries to fling them out. Balance creates the spiral beauty we see. If gravity were stronger, galaxies would collapse. Weaker, and they dissolve into darkness. This same tension governs every star. Gravity squeezes inward. Nuclear fusion pushes outward. Our sun is a controlled explosion, stable for billions of years because of this equilibrium. Even atoms are balancing acts, nuclei and electrons held together by electromagnetic and quantum forces. Without this balance, matter would dissolve into a soup of particles. From atoms to galaxies, the universe is built on tension. Catastrophic change is always possible. When balance breaks, the cosmos is transformed. These moments on the cosmic knife's edge give rise to the universe's most extreme phenomena. The universe's complexity and structure emerge from this perpetual struggle. To understand a star's survival, we must enter the quantum world. Here, particles obey the Pauli exclusion principle. No two identical particles can share the same state. This quantum rule is the universe's safety net, preventing matter from being crushed. Under normal conditions, matter is stable, but under extreme pressure, its hidden strength emerges: degeneracy pressure. In dying stars, when fusion ceases, gravity crushes the core, forcing electrons into a smaller space. Their quantum nature pushes back, halting collapse. This is what supports white dwarfs. But this safety net has limits. If the core is too massive, gravity overwhelms electron degeneracy pressure. The result, a dramatic collapse, and the creation of an object where matter is pushed to its breaking point. Quantum mechanics, not heat, becomes the last defense against gravity. The universe's strangest objects, white dwarfs and beyond, are born from this quantum resistance. When even this fails, something even denser emerges. A neutron star is the astonishing remnant of a massive star's death. Imagine the sun's mass crushed into a sphere the size of a city. A teaspoon of neutron star material weighs billions of tons. Gravity here is 200 billion times stronger than Earth's. Light itself bends under its pull. During a supernova, pressure forces electrons and protons to merge, creating a core of pure neutrons. Neutron degeneracy pressure halts the collapse, forming a new, ultra-dense object. Neutron stars spin rapidly, with magnetic fields trillions of times stronger than Earth's. Some become pulsars, sweeping beams of radiation across space. These are not just dead stars, they are laboratories for physics at the edge of the possible. Neutron stars are monuments to gravity's power and the universe's extremes. To understand stars, look to our sun. A churning ball of plasma, not solid or gas, but a superheated soup of charged particles. Most visible matter in the universe is plasma. The sun's core is a furnace of immense pressure and temperature, where nuclear fusion powers the star. Energy from the core takes thousands of years to reach the surface, zigzagging through dense layers. Above the core, convection churns plasma, creating the sun's surface patterns. The sun's atmosphere, including the visible photosphere and the hot corona, stretches millions of kilometers into space. Understanding plasma required a leap in physics. When do atoms lose their electrons? This question led to a revolution in astrophysics. The answer would come from a young physicist in India, forever changing our view of the stars. The sun's true nature is a triumph of scientific discovery. The fiery heart of stars was unlocked by scientific ingenuity. In 1920, Meghnad Saha developed a formula predicting how atoms ionize in stellar atmospheres. The Saha equation let astronomers decode starlight, revealing temperature, pressure, and composition. Saha proved that stars are so hot their atoms exist mostly as plasma. But what about matter under extreme pressure, deep inside stars? In 1926, Ralph Fowler applied quantum mechanics to white dwarfs, showing electrons form a degenerate gas. This explained how white dwarfs resist collapse, not by heat, but by quantum rules. Saha and Fowler's work became the foundation of stellar physics plasma in living stars, degenerate matter in dead ones. Their insights revealed the true nature of stars and their remnants. Degeneracy pressure is the universe's final defense against gravity. In a white dwarf, electrons are packed so tightly they resist further compression. This quantum force halts collapse. But there's a limit. The Chandrasekhar limit, about 1.4 times the sun's mass. Above this, gravity overwhelms electron degeneracy pressure. The core collapses, electrons merge with protons, creating neutrons. A neutron star is born, supported by neutron degeneracy pressure, an even stronger quantum force. Neutrons, like electrons, resist being packed together, halting collapse at unimaginable density. This is matter's last stand before gravity wins completely. The Chandrasekhar limit marks the boundary between white dwarfs and neutron stars. Beyond this, only more exotic objects can form. The universe's most extreme remnants are forged in these final moments. A star's final act depends on its mass. Sun-like stars end gently, shedding outer layers to form planetary nebulae, leaving behind white dwarfs. Massive stars die violently. When their cores collapse past the Chandrasekhar limit, a supernova erupts. This explosion forges elements heavier than iron, gold, platinum, uranium, scattering them across the galaxy. These elements seed new stars and planets. We are made of stardust from ancient supernova. If the core is massive but not enough to form a black hole, neutron degeneracy pressure halts collapse. The result: a tiny spinning neutron star, a cosmic ghost born in violence. Its creation is a tipping point where physics is pushed to the edge. Neutron stars are the universe's ultimate act of compression. To approach a neutron star is to reach the edge of physical reality. Its surface is smoother than anything on Earth, its gravity crushing mountains to mere centimeters. The crust is a lattice of nuclei and electrons, unimaginably strong. Beneath, atomic nuclei dissolve into a sea of subatomic particles, a neutron superfluid and a proton superconductor, flowing with no resistance. The interior is a quantum laboratory on a colossal scale. At the core, matter may break down into quarks and gluons, a state not seen since the Big Bang. Neutron stars are the densest observable matter, the last stop before black holes. Studying them probes the laws of physics under extreme conditions. Each discovery brings us closer to the universe's deepest secrets. The journey to a neutron star is a journey to the frontier of existence,